We are going to calculate the entropy change when an ideal gas expands from an initial volume to a final volume under isothermal conditions when the temperature is constant. To calculate entropy, we use this equation which was discussed in class, where the differential change in entropy is equal to the reversible heat divided by the temperature. If you integrate both sides of this equation from the initial to the final states, then you get a total change in entropy which is equal to 1 by T integral of dq reversible. The temperature comes out of the integral because it is constant, and this is equal to q reversible by temperature. So this is the change in entropy under isothermal conditions. However, our process may not be reversible. The problem statement was that an ideal gas is expanding isothermally from an initial volume to a final volume, and this may not be a reversible process. However, that does not matter because entropy is a state function. And a state function does not depend on the path, but only on the current state of the system, which means that we can choose a reversible path to go from the initial volume to the final volume. And this could be something like shown in this figure here. In this figure, the gas is undergoing reversible expansion, which means that the internal pressure is only slightly higher than the external pressure. In such a case, to calculate the reversible heat, one can use the first law of thermodynamics. And since the process is reversible now, we can choose the subscript reversible for heat and work. Since it's an isothermal process, the change in internal energy is 0, and this equation can be rearranged in this form. And the reversible work for an expanding ideal gas at constant temperature was earlier shown to be nRT log of the final volume divided by the initial volume, and we can plug this equation in here, and we get that the amount of reversible heat, sorry, there's a negative sign in the work, is equal to nRT log of Vf by Vi. This can then be plugged into this equation, and thus we get the entropy of an expansion of an ideal gas under isothermal conditions. It does not matter whether the process is reversible or not. Now, if the final volume is greater than the initial volume, then log of Vf by Vi is equal to log of some number which is greater than 1, and this is a quantity greater than 0, which means that delta S is greater than 0 when the gas is undergoing expansion. Similarly, if the final volume is less than the initial volume, then the entropy change will be less than 0, as would be the case